A particle is moving along a line with its velocity given by the twice differentiable. Stop right there. Sometimes you'll be reading a problem and it says all wordy, twice differentiable. Good to know because we have to have continuity, differentiability. Differentiability implies continuity, okay? So we're going to need that. Twice differentiable function v. Selected values of v are given in the table below. So there's some particle that's moving along a line, x-axis, y-axis, some number line, straight road, whatever it is, and there's a particle, a car, whatever, a snail, and we have velocity. Well, it's not a snail. We're moving at 11 centimeters per second, so it's definitely not a snail, given by this twice differentiable function. Okay, must there be a time t between 0 and 12 such that the acceleration, acceleration is the derivative of velocity, must be negative 2/3 centimeters per second. So negative 2/3 centimeters per second squared. Justify your reasoning. Okay, what in the world? Your first thought might be, I need to find the derivative of velocity and get acceleration. You don't have enough information. You don't have an equation for velocity. You have a table of values. This happens a lot, so bear with me. Must there be a time t from 0 to 12? They actually gave us an interval, so let's start with that interval. If I found the slope of velocity over time, we actually have found the same units as acceleration. Watch this. The velocity at 12 minus the velocity at 0 over 12 minus 0. Okay, numerator is centimeters per second. Denominator is seconds. This is centimeters per second per second. That is velocity. Let's keep going. Velocity at 12 is 3. Velocity at 0 is 11. 12 minus 0 is 12. We have negative 8 over 12. That is negative 2/3. And if you, again, you want to get technical about it, this is centimeters per second. So that's what we're dealing with. And then justify your reasoning. Okay, so negative 2/3 centimeters per second squared. Is this true? Is what true? Must there be a time t? Yes. Yes, there must be. How do you know? Here we go. Have we met the conditions of the mean value theorem? Let's start here. Is the function differentiable on the open interval from a to b? Yes. They said it was differentiable twice. Is the function continuous? Yes, it is, because it's differentiable. Is it continuous on a closed interval? Yes, it is. Velocity is going to be continuous on a closed interval. Okay, it is, trust me. So because we have met the conditions, we will go ahead and write a little explanation. And here's the explanation in the key of green. Yes. Done. No, I'm kidding. We are going to say that we have continuity differentiability. So v of t is differentiable on the interval from 0 to 12. We have met one of the two conditions. Met that one. And is continuous, because it's differentiable, and it's continuous on the closed interval because velocity is continuous on a closed interval. It just is. And here's what's going through my head right now. If you're like, what in the world is this guy talking about? I'm never going to have velocity that goes like this and then some awkward thing. Like, I'm never going to have this as the graph of my velocity if a particle is moving along a line. No, you've broken physics. Let's not. Okay, it's continuous on the interval from 0 to 12, and we actually are going to go a little bit further. We have met the two conditions, but they were saying, must there be an acceleration? So yes. So and the average, if I could spell average rate of change of the velocity, which will be acceleration, on the interval from 0 to 12, parentheses or brackets, not a big deal, is negative 2/3, and we'll put units for fun, negative centimeters per second per second. Okay, again, met one condition, met the other condition, and we said, yep, we got that negative 2/3 going on. Okay, must there be a time t from 0 to 12 such that the acceleration must be 3 centimeters per second per second? Justify your reasoning. Okay. I wonder if the average rate of change of velocity, acceleration, is ever equal to 3. Let's see. The slope from here to here is 7 minus 11 over 4 minus 0. Okay, let's see. Let's get this. I'm going to do several different slopes, all right? So bear with me. We're going to do 7 minus 11 over 4 minus 0, and that's going to give me, well, negative 1, all right? We're also going to do 1 minus 11 over 6 minus 0, and that gives me negative 11 over 6. I'm testing some intervals here. And now you might say, oh, from here to here, but is there ever going to be a time? So actually on this one, I found it. First try, 0 to 12. Here, I mean, you could try 0 to 12 first, which we'll go ahead and do that. 3 minus 11 over 12 minus 0, which we just did, and we got negative 2/3. Okay, yeah, but that's not it, and that's not it, and that's not it. So this slope, the slope between these two doesn't work, the slope between these two doesn't work, the slope between these two doesn't work. Let's try some different ones. The slope between these two, and you can worry yourself to death doing this. This is a little bit of a longer process, and don't beat yourself up if this didn't go through your head. No, actually, that'd be negative, and I want it to be positive. And from here to here, we could say 3 minus 1 over 12 minus 6, and that'd give me 2 over 6, so 1/3. So no. The average rate of change of the velocity is never equal to 3. I'm going to write that down word for word in just a second. Okay, you want a shortcut? I do too. Must there be a time such that the acceleration must be positive 3? Notice the rate of change. This is decreasing. So from 0 to 6, we know that the velocity is decreasing. So the acceleration, derivative of velocity, will never be positive in this interval. So all that checking I did from here to here and here to here, which I don't think I did that one, did I? Yeah, I did. And from here to here, like, nah, not necessary. Not necessary at all. I can check some of the other ones, but I've checked every possible set of points that I could come up with. Did I do 3 and 7? I didn't. I didn't do these two, but it's still not going to work because overall it decreases, right? It's simply going to decrease. If I'm going from 7 and I end up at 3, it decreased, and I want it to be positive. So really the only pair of points that I have to check are from 1 to 3 because that's the only time it'll increase. And that didn't work. That gave me 1/3. So let's put some things in nice, neat verbiage. So no, there will not. The average rate of change of the velocity is never equal to 3 on the interval, no matter how we try it, interval from 0 to 12. Okay? Closed door open, not going to be picky about that. All right, you ready for a little bit of shifting gears here? I am. Must there be a time t from 0 to 12 such that the velocity must be 2 centimeters per second? Justify your reasoning. I wonder if the velocity is ever 2. Okay, well, first of all, we are asked about velocity, not acceleration. What are we given? Velocity. Okay, I told you when we were on the front side of this page right here that the mean value theorem is an existence theorem. So if we've met some conditions, we have something that exists. But they're not asking us about average rates of change. They're asking us if the velocity exists when they give us velocity. Will I ever in this continuous function, differentiability implies continuity, will I ever in this continuous function have a velocity of 2? Maybe not here, but definitely here. and definitely here. I could have said, at how many times must the velocity, at least how many times must the velocity be 2? Twice. 1 here, 1 here. Somewhere between 4 and 6, somewhere between 6 and 12. All right, let's write that down. How do we know? The intermediate value theorem. And because the light is coming through the window as I record this. That's why. So, yes, there actually are 2 times. And let's put our reasoning. And we are dealing with another existence theorem that we've already learned. Yes, because, first of all, v of t is continuous. I want to word this a little bit better. All right, sorry. Going to use a little bit of whiteout. I want to word this like a free response question. Because velocity is differentiable and therefore continuous. Would you get points off for that? I don't know, but it's a good idea not to just say it's continuous. How do you know? You know it's continuous because it's differentiable. Therefore continuous. And because, all right, I'm thinking back to some old notes that I would love to dig out right now, and I don't know if I can find them. But because we have met the conditions for the intermediate value theorem that I'm furiously flipping through my notes to try to find, because we've met the conditions for the intermediate value theorem, which are betweenness and continuity, then I can't find the notes, and we will just proceed. We have continuity, let's get betweenness. Because 2 is between 1 and 7. I'm going to call it a little bit differently. I'm going to call it v of 6 and v of 4, sorry. V of 6 is actually the small one, and v of 4 is the big one. And we have some more betweenness. We have some betweenness going on here, and it's between v of 12 and v of 6. And 2 is between v of 12, that's the bigger one, and v of 6, which is the small one. The intermediate value theorem, you can abbreviate it on the test, applies. Okay. Must there be a time such that the velocity must be 0 centimeters per second? Justify your reasoning. No. All right, here goes. Asking about velocity again. Does the velocity exist to be 0? Is the velocity ever 0? If it is, it doesn't show up, so we can't guarantee it. Must there be a time? No, because 0 is, I don't know why I have that big gap there, not between any of the y values, any of the velocities that I've been given. I'm going to just go from one extreme to the other. 1 and 11. Those are my lowest and highest velocities that I've been given. I'm going to write that down, which are the maximum and minimum, minimum and maximum, minimum and maximum velocities given the intermediate value theorem does not apply. How sad.